All right, the recording has started. Deniz, the stage is yours.
Okay. First of all, thanks for the organizers for letting me talking here. And so today, as you see, today I will going to speak about this problem, which is kind of a problem I go back and forth from my PhD days. So the first paper is in 2014, as you see. Then I come back to this problem again, since I had the time and I had other motivations and I will be talking about. And so, yeah, the problem today we are going to speak about is mostly on Lipschitz spacetimes, and by colored Lipschitz spacetimes, I mean the Lipschitz spacetimes that are solutions to Einstein-Yang-Mills theory, okay? So let me go over the contents. So I will first give an introduction to Lipschitz spacetimes, okay? And I will talk about the previous works and models related to our problem and the motivation. And I will also talk about a little bit more about the Lipschitz holography maybe, although I won't give you any explicit details and computations so on. And I will just talk on what people have done, and I will talk about the interesting points for me. Then I will review the Einstein-Yang-Mills solution, the previous solution I have found before, like 2014. And also, besides Lipschitz solution here, there will be some black hole solutions, numerical black holes, and I will discuss about those. Then I will pass to the new work, and which is about first constructing a variational well-defined action. Then I will give some definition of the non-relativistic boundary stress tensor, and then using this stress tensor and other well-defined action, I will show that these quantities like stress tensor and well-defined action will remain finite. They don't explode or something goes bad when I consider perturbations around this Lipschitz solution. Then I will compute the mass and the thermodynamics of these black holes and check if they satisfy the thermodynamic relations. Then I will talk about the summary and the future problems. So let me start with the Lipschitz spacetime. So Lipschitz spacetime actually comes from, it was known before, but it was kind of made popular after the Untitled Chapter holography, okay? So a great deal of non-relativistic systems exhibit dynamical scaling at the fixed points of their renormalization group flow. So if you remember from the previous summer, if you have been to summer courses and so on, Soner talked about these critical points and all those scaling invariances and conformal filters and whatnot. So for Lipschitz spacetimes, we will consider, just forget about Lipschitz spacetime. So some condensed matter systems may exhibit this kind of scaling at their critical points, right? So that is lambda to the z. So when z is equal to 1, this goes to conformal scaling, right? So this relativistic stuff Soner talk about mostly. Then, and a classic example is the Schrödinger equation, right? Schrödinger equation falls into this class with z equals 2, and it has a quite large symmetry group. When z equals 2, it is quite larger. It has a quite larger symmetry group. And another canonical example is this Lipschitz field theory. It has again some z equals 2 symmetry, like here. So after the success of Untitled Chapter holography, so imagine you have a key, right? So people thought they have a key and try to find a hole to stick it around, right? So because they know from the Untitled Chapter holography, they can compute some correlation functions, the energy or whatever, the word identities and so on for quite complicated systems. And they can use the gravity side of it. So they thought using this symmetry group and using this symmetry group, can we get a space-time so that we have this symmetry group, right? And this following the logic of gauge gravity duality, they look for the space-times and that enjoys this anisotropic scalar invariance. And the first papers are like from Kahru, Son, and Akrivi, and these other guys. So then they succeeded constructing these Lipschitz spacetimes and something like this. So they have set of these generators or set of this symmetry group, something like this. So they have the dilatation, right? They have the rotation, and they have these PI is the translations, and they have this H is the translations in time, and they have this Z dynamical scaling Z. And if you look closely, you don't have these boosts, right? So Galilean boosts and so on. So this is quite simple, and this looks to Lipschitz spacetime, which is our topic today. But so Z equals 1 corresponds to ADS, which is quite well known. But if you want to have more symmetries like the Galilean boosts and something called spatial conformal symmetry, you need to extend this algebra more, right? So given extending the symmetries to Galilean boost, which is Z equals 2, you will have this larger algebra. And this larger algebra will lead to something called Schrödinger spacetimes. And these are also so-called the non-relativistic spacetimes because of the fact that, people showed that and kind of not actually proven, but shown that these bulk spacetimes has at the boundary, they have some non-relativistic theories, okay? Unlike the anti-de Sitter holography, where you have some conformal field theory on the boundary, and in the bulk you have anti-de Sitter. Now you have these guys, these spacetimes like Lipschitz, Schrödinger, and they have different field theories on the boundary, living on the boundary, but those theories are non-relativistic theories, right? And for Z not equals to 2, you need to throw away the spatial conformal generator, and you can generalize this Schrödinger spacetime as such. So I'm not going to talk about these today, but we will return back to Lipschitz. So you need to have some kind of matter or higher curvature terms, or some kind of matter to have Lipschitz solutions. So they are not maximally symmetric spacetimes, right? So they lack most of the properties that ADS has. And the most studied model is the following. This guy studied by Kakru and in this first paper. So they studied this two-form and three-form coupled theory because it has some relation with the string theory. It comes from the higher dimensions and so on. And they studied with the 4 dimensions. But later, this was shown that at D equals 4, you can integrate out the 3-form field and end up with the massive scalar, and not massive scalar. I forgot the name. What was the name for this one? Proca model. Proca, right. So this Proca model, right? So this is the most studied model because it is quite easy and it has some higher dimensional origins. As I written here, these for Chern-Simons couplings and massive vector fields generally arise in string theory compactifications, and this guy has a nice property that it comes from some kind of spherical compactification in the higher dimensional models, right? And I'm going to show that this property is quite useful when discussing the holography of these Lipschitz spacetimes. And as I written here, this spherical compactification, this is exploited in these papers in order to show that on the boundary, there is a Newton-Cartan geometry, right? So the interesting thing is these spacetimes has on the boundary, they don't have a degenerate metric, right? Unlike the ADS. In ADS, you have a non-degenerate metric. You have Minkowski and whatsoever, but in here, you don't have this Riemannian geometry. You have something called Newton-Cartan geometry with a torsion, and it is quite nasty to work with, but it is the way it is. You can write field theory, non-relativistic field theories using these Newton-Cartan tools, okay, which I'm not going to discuss today, but this is quite interesting. So in these 3 papers, and there are a lot of more, people discussed what is on the boundary and how they studied Lipschitz holography. So just to give some summary of these 3 papers, that we show several more slides about and talk this Lipschitz holography. So let me talk about the Pfefferman-Graham expansion and Z equals 2 Lipschitz from ADS5. So in order to talk Pfefferman-Graham expansion, I don't know if somebody talked about this before, maybe Gizemto, I don't know, he was talking about the holography, but so this Pfefferman-Graham expansion is an important tool in holography. And to define this guy, let me talk about first this conformal infinity thing, and probably people have talked about this before me. And in a nutshell, the idea is related to physical metrics.
We haven't discussed this part. I mean, neither me or Gizem, okay. So maybe you can spend more time on it.
You didn't talk about FG expansion, right?
No. It says we have focused on the isometries of the groups and this conformal infinity, but not the FG expansion.
Okay, I will just give you 2 or 3 slides, just a quick one. I don't have much anyways. So this, it is, the idea of the conformal infinity. So you basically, which is from Penrose, and it is quite nicely summarized in this book. And I think there are more simple books, but this is the main thing. So for the conformal infinity, you scale your metric, right? Your metric G mu without tilde, with a scaling factor lambda square, and this, omega square. And this omega square has this scree is the boundary, right? On the boundary, this omega should be 0. And this d of omega should be non-zero, and omega at the bulk should be greater than 0. Okay, this function has to satisfy these properties to conformally extend and write the conformally extended metric, this G hat guy. So this thing is quite useful, and as an example, you can take ADS as an example. The first on the first line, there is one incarnation of the ADS. This is quite well-known one, and you just do a transformation to this variable, and you end up with this metric. This is still ADS, but it is in the nice form that like this above form, right? This, if you define omega as 1 over cosine, and you will have a simple pole, and the derivative is non-zero, and it is in the bulk it is greater than 0. So this is the omega v1, and then the piece inside the parentheses will be your boundary metric when chi is equal to pi over 2. So you have this boundary metric is I think it is called Einstein space. I'm not sure. It should be. Anyway, so you can do this conformal infinity trick, and I mean you can define this conformal infinity. You can find the boundaries well for the ADS spacetime, right? But for the Lipschitz, things will change. And what is important about this boundary metric is the energy momentum tensor of the dual theory is sourced by this boundary value of the bulk metric. So it is crucial that you can determine the boundary metric, and you can vary it, and whatever you can do, you can play these holography tricks on it. And for the ADS, we can give 2 definitions. So we can, for the asymptotically ADS spacetime, we mean spacetime whose boundary is equivalent to that of ADS. And this is the Schwarzschild ADS as an example. So F is this guy, right? So when R goes to infinity, or when R goes to the boundary, you will have the exact ADS time, right? F goes to 1, so L squared over R squared, then you will have the ADS as the boundary. But you can generalize this asymptotically ADS concept and write down the asymptotically locally ADS, right? And you define this asymptotically local ADS stuff as where you have the Riemann tensor. You sit down and compute the Riemann tensor of a given spacetime, then you will see that it has the following form, right? You will have d of omega, some some function like this, and you have this good maximally symmetric piece, and you have some higher order terms. And basically, this asymptotical local ADS definition helps you to compute the holographic quantities, right? Like the energy momentum tensor and so on, because you can define perturbations around this ADS spacetime, and the very important result which holds this for just a second. Okay. So you see this. Okay. The very important result which holds for these asymptotical locally ADS metrics is given by Pfefferman and Graham, right? So they show that any asymptotical local metric has an asymptotic expansion near the boundary, like this one. So you have some kind of metric, any asymptotical local ADS metric. That's the condition. And you have this HAB piece is expanded as such, right? So you can write this down. This is really important for holography, because you define this at the boundary. You will define some perturbations and so on. So you need to know how the metric goes on the boundary, okay? And this is mathematically proven. And this Pfefferman guy has a Fields medal, if you don't know, and he's quite a solid guy. And I don't know much about Graham though. And in this paper, this is an old paper, 85, and so physicists didn't use this before, I think, but who made it famous is written in his ADS-CFT paper, this one, and you can find good discussions in Skanderis lectures notes on holographic renormalization review paper. So this is quite a fundamental, let's say, expansion or theorem in this holography stuff. So as I have written here, in this expansion, HAB is the boundary metric, right? Leading term in the expansion. Then by plugging in this expansion into the field equations, and you can find these coefficients, H2AB, HD, and so on, in terms of the boundary metric H0, okay? And in general, as I've written here, this HDAB will be related to energy momentum tensor, and the other terms are related with the anomalies, okay? So that you can find the anomaly of the field theory on the boundary, and you can find the energy momentum tensor by just working with the bulk theory, right? And using this Pfefferman-Graham expansion and so on. So this is really, yeah, sure.
By anomaly, are you referring to the anomaly in the sense of quantization?
These conformal anomalies, right?
Oh, okay, so it's about the algebra.
So just a second, I'm lost. Okay, unfortunately, this Pfefferman-Graham expansion does not work for the Lipschitz spacetime, right? Because as I told you, this whole construction works for the ADS and this asymptotical local ADS, this Pfefferman-Graham thing, and even the Lipschitz is not maximally symmetric. So in turn, this makes it rather difficult to perform this holographic renormalization, or you cannot define these sources, these vacuum expectation values, and other things you do in holography. But instead, there is something called concept of anisotropic infinity, like the conformal infinity I have defined before. And this is given in this paper. I read several times this paper, but in computationally, it doesn't say much. So I don't know, and people didn't use it. So it works as a conceptually, it works, but there is nothing like the computation that it doesn't give you something like Pfefferman-Graham expansion. So in order to work this, in order to find what's going on the boundary, people use a different method. So they start from the supergravity in 10 dimensions, okay, containing this axion dilaton field and a 5-form field strength, right? This doesn't have an action, just the field equations, okay? So this is studied in these 3 papers. They start from 10 dimensions, then they use some compactification and they go to 5 dimensions, okay? They're using the Freund-Robin compactification. Then this equation of motions follows from these actions, these 5-dimensional actions. From the reduction, you have something like this, okay? The good thing is this has an ADS solution, okay? It has an ADS solution. You can do Pfefferman-Graham expansion. You know all the tools. You can do renormalization, whatever you want to do. And I also didn't tell you, but you can expand these scalars and these gauge fields with like a similar expansion, like like an FG expansion, right? You don't need to just expand the metric. You also need to expand these guys. But these are well-defined. So they studied this ADS solution in 5 dimensions. But if you look at this chi field, and it is translational invariant, right? It doesn't appear on the exponentials and whatever. So by using this translation invariance, they do one more reduction, okay? This from 5 dimension to the 4 dimension, okay? And then they will have something like a Einstein plus Proca and some other terms, some other fields. But basically it is Einstein plus Proca from these big D's means you have a mu's in here. So from this 5-dimensional solution, they go to 4 dimensions. And this good thing is this 4-dimensional model has a Lipschitz solution, okay? So what they do is they know the 5-dimensional ADS solution, right? And they studied the holography. So they related those quantities which are computed in 5 dimensions with the reduction ansatz to 4 dimensions, right? So they can work 4-dimensional Lipschitz theory by using the 5-dimensional Pfefferman-Graham expansion.
Deniz, just a question. You just use the dilaton and the vector to realize the solution, right? Dilaton and the vector. Yeah. So chi and small phi, they just, one is 0, the other is a constant. Okay.
Yeah.
So I didn't write the usual solution that we already know.
Yeah. This is for some choices like phi 0 is constant and whatever so on. It is the usual Proca solution we already know. Okay. So the way they studied holography is like that. So they know the 5-dimensional, and the only way they can study at that time is this way. And I think up to now there's no much developments on this area, I guess, as far as I know. So yeah, they using this reduction, they can compute all the stuff they wanted. And yeah, these are the guys that did it, these Oberts and Hartung and Rollier and Christis. And they have shown that there is this torsional Newton-Cartan structure, which is quite complicated, but it is needed. And most of the things I discussed here are given in this really good thesis by Morten Holm Christiansen, and this on the charge case, this Emil Harris thesis. These are really quite good. And if somebody, I mean, even if you are just wondering about this holography and this holographic renormalization stuff, you can read these theses, and some of the computations are quite helpful. Also, you can watch the Pfefferman's lecture on conformal invariance. He's quite a good lecturer and quite a naive guy, and it's a really good lecture. I suggest you to watch this one also. Okay, about the holography, that is all I wanted to talk. And as far as you see, so there is since you don't have this FG expansion, you are kind of in a bad position to know about this boundary behavior of the solutions, right? So you need to either devise ways like this, or you need to bend some of the ADS tools and exploit some of the ADS tools to discuss about Lipschitz. So, and one more thing about this Lipschitz holography. So I guess before me, people have discussed this for the ADS holography, and for the ADS spacetime, the time-like geodesics cannot reach the boundary, right? The null ones reach the boundary and they can turn back. ADS behaves like a box, right? But for Lipschitz, even null geodesics cannot reach, I mean, null geodesics can reach the boundary if their transverse momenta is 0, if they are radial. So not all null geodesics can reach the boundary. So if you want to construct from bulk to boundary things, and you lose some info, right? And these non-radial geodesics will experience a great.
May I ask a naive question?
Yeah.
So you say that, okay, there are some kind of these null geodesics with non-zero transverse momenta, and they don't reach the null boundary, right?
Yeah.
So, so when I take like the affine parameter, like let's say I'm parameterizing them with some parameter, I'm taking the parameter to infinity. Where would exactly they reach? Like, are they?
I think they will turn back. So in this paper, so in this under this construction of Lipschitz spacetimes, they have nice graphs, right? So they start with some momenta that null ray goes to boundary, then it turns back, and it turns back, but it cannot reach the boundary. I mean, it doesn't turn back without touching the boundary, let's say.
I presume that the turning point kind of depends on the transverse momenta. So when I take transverse
momenta, and the potential and Z and all this stuff, I think.
Okay.
So,
that makes sense.
So so things doesn't work quite well, and I don't know if this Licious holography and this non-relativistic holography is really working well as the ADS. I mean, even ADS was not proved, but this one has bigger problems, right? So you can find the problems on the reconstruction and what do you lose and these pathologies of asymptotically Lipschitz spacetimes.
Can I ask a question here?
Yeah.
What does it mean the null geodesics can reach the boundary if the transfer momenta is 0? What do you mean exactly? I don't understand.
So in ADS, as far as I know, the null bound, I mean, if you are in the center of the ADS and send a light signal, right, to the boundary, it goes to boundary and touches it and comes back, reflects back, okay? So by the way, if I'm saying anything wrong about this, just let me know, because I'm not an expert on this holography stuff, but
well, actually, let's just say, I mean, it's something crucial for usual formulation of the holography to work. So let's put it that way. Of course, I mean, what he's saying is not physical, right? He says, okay, we are able to reach infinity at a finite time, but it is the case for ADS. And in the so that's the thing. I mean, for ADS, it works and it has some role in the formulation of holography. So here it is only partially satisfied.
I think you don't even need to reach at finite time. Like in Minkowski space, you do not reach null infinity at finite time. But
but that's why you need all these extra machinery, right?
Yeah, that's true. So, but you still have kind of holography there.
So it's like an important difference compared to ADS.
Yeah, that's true.
Yeah. Okay, so it's okay. Back. Okay, let me turn back to my problem, at least from the Lipschitz holography. So the main motivation to come back to this Einstein-Young-Mills problem. First, I have the time, okay, because of COVID and stuff, and being in China, I had at least 1.5 months in quarantine, so I had a lot of time. And second, this group has contacted me saying that they have used this Einstein-Young-Mills solution appearing as an IR solution to these holographic flat bands. So somehow that people have managed to construct something useful or something physical, let's say, which involves graphene and so on, which I don't know much about. And they asked me some questions about the solution and stability and whatsoever. So I decided to come back to this problem again. And let me review the solution now. So with these things in mind, and in order to extend this Lipschitz holography to other matter fields, like as I told you before, it was only studied in like Broca fields, right? So I consider this Einstein-Young-Mills section with this SU2 fields. So this is the solution part. And this is the action, right? Einstein plus some cosmological constant plus some SU2 pieces here. And this trace of F mu whatever. And these T's are the generators, where taus are the Pauli matrices, and these big lambdas, sorry about this lambda and lambda same, but these big Greek letters and capital Greek letters are running over the group indices, and these mu nu small Greek letters are space-time indices, and we are working on specifically on 4 dimensions, okay? So the field equations are, you can easily find it as follows: this Einstein piece plus this T mu nu piece, and where T mu nu is given like the Maxwell one, but with the traces, right? And these are given as such, like you have this SU2 piece also. So this cosmological constant is quite easy to find, because if you consider a Lipschitz solution in the form like this, by the way, I'm going to throw away this R piece to the end, because I'm going to go to boundary from the radial direction, right? So I'm just throwing all these to the final entry, this R, and this planar part is, this spatial part is planar plus some time T time. And I'm not going to consider the spherical case in this paper, but in this work, but in the previous paper, I also considered this spherical and so on. Now you consider this Lipschitz solution of the form, and it is really easy to find the cosmological constant. You just take the trace of the previous equation, this equation, okay? When you take trace, this T trace goes away because of conformal invariance, and then you have this Einstein piece, then you can find this lambda as such, right? Lambda. So for z equals 1, you need to find you need to go to ADS path. But for the rest, you need the planar symmetric Young-Mills ansatz. I just giving you the matter field as SU2, but as you know, this SU2 field has many entries, right? So for the rest, you need to know how the planar symmetric Young-Mills ansatz goes, and this is quite an interesting problem. You can check these references, and I recommend you this Jacob's book, which has a quite nice example. So the problem you have is more general, right? So you have some gauge field, and you have some space-time, and you want to find a gauge field that obeys the symmetries of this space-time, okay? So that what is the most general gauge field that obeys the symmetries of the space-time you are working on? Like if you are working on spherical symmetry, if you are working on planar symmetric and whatsoever. So the basic idea is as follows: as you know, these gauge fields transform finite in finite transformation. They have this form, okay? Then you also have these space-time symmetries. Let's say these are the killing vectors of the space-time, and this is the transformation of the gauge field. Then if you look at this finite transformation in infinitesimal form and take a Lie derivative of A mu, the right hand, there will be some term right hand side, okay? I call this omega, and this is a function of the, this is SU2 valued function, let's say, okay? So for normal vectors, this should be 0, okay? But for gauge fields, there is some gauge degree of freedom, and it is hidden in here, okay? And if you work it around a little bit more and take another Lie derivative, you will see that this omega function will satisfy some compatibility condition such as this. And from this, if you work it a lot around these equations, you will see that you can find this omega and the most general form of the ansatz you are working on. And as I told you, this Jacob gives a nice U1 example for the spherical symmetry and I guess the planar symmetry, how this whole machinery works, okay? This is quite an interesting problem. Anyways, or you can just go this paper and find the Young-Mills fields invariant under subgroups of the Poincare group. And then this paper will tell you that the planar ansatz is the following, right? The most general ansatz is this. And if you want to see it in a little bit more detail, this is the ansatz. Okay, I just expanded this in terms of these t's, right? 0. So this is so r is here. So this is time, this is x1, x2, and r. So I throw r to the end, r coordinates. So this is x1, x2, x1, x2. So there is a symmetry in changing x1 to x2 and t1 to t2, right? So if you change x1 to x2, you need to change a2 to a1. And this q corresponds to electric SU2, right? So in this problem, I will set q equals to 0, okay? Then I will only work in the magnetic part. So this is actually the magnetic. This is called the magnetic part. If you compute the F mu nu, then you will find that you will have only the magnetic pieces. And this whole Leafy solution is as follows. You go to the field equations and solve. It is quite easy to solve now. And you can see that for R equals like plus minus sigma R, which plus minus comes from the gauge invariance, gauge degree of freedom. And for all Z greater than 1, this is the solution. And this is the cosmological constant, and this is the Yang-Mills coupling. So what happens at Z equals 1? What happens is at Z equals 1, you go to ADS, right? Then you go to, as you go to ADS, these G Yang-Mills appears as 1 over G Yang-Mills, so it will decouple. So you just have the cosmological Einstein now. At Z equals 1, all the structure will decouple. Then this solution is later extended to D equals 5 by Hongyu and his graduate student, I guess. And at D equals 5, you have a more structure, right? You have T1, T2, T3, and it has more symmetry. But the basic idea is the same. You have a similar solution. And this Einstein-Yang-Mills solution one has one interesting thing, which is related to the things I have talked about before. This has a relation to higher dimensions, okay? So this solution can be embedded in D equals 11 supergravity, and one problem you can ask to yourself is, can I do this? Can I use this embedding like the massive vector model, like people have done before, and compute these all the things they have done in this PROCA model, right? So they have computed this holographic stuff using the ADS solution in the higher dimension. So can I do some such thing? That is one question you can ask. But in this paper, we will turn back to defining a energy momentum, defining energy and stress energy tensor at the boundary for this model, okay? Because I also have some numerical black hole solutions for this model, but I don't have exact black hole solutions. That is one of the things with the Einstein-Yang-Mills. I don't remember exact black holes. I don't know any exact black hole solutions for Einstein-Yang-Mills system. There are only numerical ones, and I will talk about them later. So let's go to the definition of the well-defined action. So we have a solution in hand, and now consider the variation of the action, okay? You have this action, and you know the solutions, and you want to define something on the boundary, okay? But to define it, to well define it, you need to first get rid of the derivative of the variations. So if you vary this, you will have field equations, okay? Then you will have some total boundary term. If you have done, you will remember this. Then you will have this guy is the variation of the Ricci, actually, and this comes from the variation of the matter fields. This guy has some problems because it has the derivative of the variation, but this is quite famous term, and it can be get rid of by adding the Hawking-Gibbons term, okay? This F mu guy, you can kill this guy by adding something on the boundary. So this is the original action, and this is the boundary, guys, the second line. So this 2K handles this F mu part. F mu is given by Christoffels and so on. K is the extrinsic curvature, which is defined as the normal, derivative of the normal symmetrized. And normal is, I'm going to boundary, as I told you before, I'm going to boundary from the radial direction, okay? This is because in the sense of the holography and so on, I'm going to go to boundary in the radial direction, not time direction. And this 2K is the Hawking-Gibbons term that kills out this guy. But I also need to such thing that this variation of the whole action should be 0 on the solution, okay, on the Lipschitz solution. So in order to handle these extra terms that are generated, I added this K0, which I don't know for now, and alpha, which will be fixed. And this is the boundary term coming from the matter part. So for Einstein-Young-Mills, this boundary term is quite well fixed because of the gauge invariance, right? But because of the gauge invariance, you cannot write much different terms in here. But in Proca, you can play around a lot of more. So this is quite fixed. And if you vary these boundary pieces, this 2K plus K0, this 2K was Hawking-Gibbons, and it will give you minus n mu, f mu, and mu. As I told you, this will kill the derivative of the variation, and this will give you the other pieces give you this punch, and this is the momenta. But we don't care about for this one. And the second part is you can easily vary these, and you will find something like energy momentum tensor plus some extra pieces. So by plugging in the okay, it is also good to define the following boundary tensors, right? So we gather these delta gammas in some SAB term. So delta gamma SAB is this guy, and SA lambda with a matter with the SU2 index is this guy. So I just gather around these guys. Where EA is FAB, and I think I didn't write it here. Did I write? No. So this EA is normal contracted with the antisymmetric field tensor FAB. Okay, this is something you know. What I don't know is alpha, this constant, and this K0 around somewhere. It should be somewhere around here, but I don't see. Yeah, this K0. So by plugging in the Lipschitz solution, you will see that K0 should be Z plus 3, and this alpha should be Z plus Z minus 1 plus Z plus Z minus 1 over Z plus 1 square, so that this full variation is 0 on shell, okay? So if you start with this action, okay, hit some variation, del S to it, and you go to Lipschitz solution, you will see that delta S is exactly 0. So this is kind of important to construct because of the finiteness of the energy, stress energy tensor we are going to discuss on the boundary. This is kind of the, if you think of, if you remember the asymptotical locally Lipschitz and asymptotically ADS and asymptotical locally ADS difference, it is kind of, here we just go to asymptotically Lipschitz ones. We are looking for the asymptotical Lipschitz ones, and we compute the well-defined action for these guys, right? So for another project about this problem can be consider the more general Lipschitz spacetimes, okay? Something like asymptotical locally Lipschitz spacetimes. Then try to find this action that is variational well-defined, meaning you need to do holographic renormalization on this one, okay? But here, this is the most simplest one I can write down. And yeah, this is the thing I was discussing. So if you consider more general Lipschitz spacetimes, you should consider this. You should consider something like this in this paper, okay, that Simon Ross did. And as a side note, consider this boundary term, which we did consider this one, but you can also consider this guy, which is considered in Brown-York paper, and which actually I started with this, but if you go a little bit, if you do a little bit computation, you will see that this is not gauge invariant for SU2, okay? This has a problem. On shell, it is gauge invariant for U1 cases, I mean the Maxwell cases, but for SU2, this doesn't work. And there could be some derivative of F boundary terms, right? I could consider derivative of FAB, derivative of FAB, and this comes in if you consider more general Lipschitz spacetimes, okay? For now, we stick to these guys. Okay, let me go quickly to stress tensor for these non-relativistic theories. And this section is based on this paper. Okay, so this definition, this following definition, this one is sufficient when the metric is only non-trivial boundary field in relativistic theory. So first, let's start from the relativistic consideration. Okay, this is for the ADS, for example, and actually this discussion comes from this paper from Perkraz and this guy, a stress tensor for antidescriptive gravity, and this is one of the papers that is at the beginning of this holography stuff. So when you're at the relativistic case and you don't have any other method, just the metric, you can use this one. But later it was shown that if you consider some extra method, like even in ADS case, you will see that this doesn't work. Okay, this first one doesn't work. And you need to extend this definition given by these three guys when theory involves extra fields other than scalars, something like gauge vectors and some other spinors, even spinors, I guess. So for that, you need to consider some field binds at the boundary. Okay, like this is the Minkowski guide, and this is the field binds, and this is the paper, by the way. So that with these field binds, you can write any boundary tensor as follows. Okay, so you take all the geometric stuff into the field binds, and you leave this xmn will be fixed. Okay, this tangent space components of any vector will be fixed. So you can't use this first definition. You will just use this one, and you need to decompose all the boundary fields as such with their field binds. And in the case of ADS, this choice of frame fields correspond to the Pfefferman-Graham expansion we have taught before, right? So all these things are connected to each other. And then you can define the
Deniz Hocam, Gökhan beni duyuyor musun?
Duyuyorum. Ben de sana yazmıştım. Bende mi sorun var, Deniz mi dondu diye.
Fark ettim. Ben de kontrol amaçlı buradan sordum. Belki bize donmuştur diye.
Hay Allah.
Bize donmadı, garanti birbirimizi duyduğumuza göre.
Tamam, ben Deniz'e Telegram'dan yazayım.
Tamam. We apologize for the inconvenience. Is there anyone here who doesn't speak Turkish? Actually. Zaten bitmek üzere gerçi 15 dakika sonra ama. Zaten şey demişti Deniz hocamız, duymayanlar için, sonra katılanlar için kendisi Çin'den katılıyor. İnternet bağlantım çok iyi değil demişti.
Kamerayı kapattı, o da fark etti sanırım.
Evet.
Tüh, en heyecanlı yeriydi.
Ekran da kapattı paylaşmayı. Düştü mü acaba, düşmedi burada. Belki o bizi duyuyorduk da biz onu duymuyoruz.
Vallahi şu an tekrar geldi Deniz.
Evet. Keşke önce konuşsaydı ya. Bizi duyuyor musun Deniz? Şöyle yapalım Gökhan, Deniz'den notlarını isteyelim her şekilde. Silah'a koyalım.
Tabii onu koyarız zaten de hani sonuçta bir 15 dakika var. Devam edebilme şansımız var mı acaba?
Evet, süper olur da hani en kötü olasılıktan başlayalım düşünmeye de. Ne demezsek? Edersek süper. Hocam ekranı paylaşmadan sadece hani en azından bir yani wrap up bir şey yapsaydınız o da olur. Sadece sese yetiyorsun internet. Bir chatten yazayım bakayım. Acaba bir şey mi oldu ki? Gökhan sen yazmış mıydın kendisine ayrıca?
Telegram'dan konuşuyoruz biz. Oradan yazdım da.
Döndü mü?
Yok. Görmedi bile.
Buradan bir yazayım.
İnterneti bayağı kötü olabilir.
Evet. Hocam burada mısınız diyeyim. Yani burada olduğu belli gerçi. Ekran paylaşma çalıştı.
Şansa bak.
Geldim dedi. Tamam. Ekranı paylaşmadan konuşsanız önce.
Evet, sesi hiç duyamıyoruz Deniz şu anda.
Duymuyoruz. Sen bizi duyuyorsun galiba.
Evet, biz seni duymuyoruz Deniz.
Bizi duyuyor musun? Evet, duyuyor tamam. Biz seni duymuyoruz Deniz. Ekranda önce ses ayarsak daha güzel olacak sanki.
Ekran paylaşmakta zorlamaz ki canım. Yani.
Ekran video ya, o açıdan söyledim.
Ha, anladım.
Ben daha çok bandwidth. Sıkıntının bilgisayarın değil, internette olduğunu varsayarak konuşuyoruz gerçi ama. 3000 RPM'de dönüyor fanı. Çok sıkıntı değil herhalde 60 derece. Yok, gelmiyor.
Gelmiyor Deniz.
Sen bizi, önce ben size bilgi vereyim sen bizi duyduğuna göre. Biz ekranı görebiliyoruz. Kameran kapalı, ekranın açık.
Şeyi görüyoruz. Browser'ı görüyoruz.
Aynen. Görüyoruz. Evet. Her şey çalışıyorsa ekranı değiştirebilir misin PDF'e tekrar? Hiç olmazsa onu görelim. Tamam. Bir tek sesi sıkıntı var. Kaç sayfa kalmıştık acaba? Üzerinde voiceover mu yapsak diye düşündüm. Geldin Deniz. Kameran da açıldı.
Geldi mi ses şimdi?
Ses de geldi.
Tamam, süper.
Deniz,
Tamam,
15
çok
dakikan
ilginç.
var.
Tamam. Nerede kalmıştık en son?
Şeyi anlatıyordun işte. Field by'ını boundary'de tanımladık.
Okey. Ya
Tamam,
buraları
doğru.
anlattım mı size?
Burayı anlayabildik en son.
Ya şu XAB decomposition'ını anladın mı? Tamam.
Ben ama zaten
Geldi.
biliyorum, hani bana sorma.
Yok yani geldi mi size buralar?
Geldi.
Okay, so let me turn back. I hope it doesn't go away. Anyways, you can define this boundary tensor with the variation of the field bind. Okay, you shouldn't vary the metric. The point is you go with the field bind, right? Then you can write the variation as follows. By the way, just warn me if you don't hear anything, okay? And the conservation is also modified, okay? So this is something you can check from the paper. I think I have given the paper before, right? These guys. This is quite a rigorous paper and a good one. But we were still on the relativistic side, okay? So what we need to consider is this following. So in a non-relativistic theory, instead of the energy momentum tensor, you will have this energy density, energy flux, and the momentum density, and this spatial one, okay? Everything is distorted. I mean, everything is, let's say, not covariant, okay? Not covariant enough. So, and they should satisfy these relations, okay? Z times epsilon and so on. And the main idea behind this construction is you just take the non-relativistic of limit of these previous guys, this Ishibashi, Marov, and the other guy,
so that these identities can be derived as a non-relativistic limit. And for a consistent limit, there are two important stuff. So you should scale this field binds with power of r so that they stay finite. Okay, like this. Okay, this at the boundary. This E hat is at the boundary, and these E's are at the bulk. Then the Lipschitz background solution is this condition. Okay, so that's the only difference with the relativistic case. And now you can use these scaled fields and as the boundary data and take the variation of the scale, these scaled ones, field binds. Okay, this is the first line. Then you just expand these A's and B's and you define the energy momentum as the 0t component of this guy. And the momenta is EIT of, and spatial is this guy. So at the end of the day, you will have these components of these energy momentum tensor, okay? And after finding this one, you will just plug in these SAB and SA lambda I have found before into this one, and you can find the energy and momenta and whatever you like for your solution, okay? And for this, I will, after this point, I will study the perturbation and the black hole solutions using this energy momentum, not energy momentum, stress energy tensor, let's say, okay? Or this is called stress energy complex. So how much time do I have?
10 minutes.
10 minutes, okay. So let me go quickly over the perturbation analysis. What I basically done here is I have this stress energy tensor, right? Which is for the Lipschitz solution. I just do small perturbations to that solution. But for the perturbation, there are two difficult things, okay? First, you need to define these field binds, right? So these HTT and V's are the perturbation. You have to be careful about choosing the perturbation. And on the matter sector, you have to be more careful because of the background symmetry plus the gauge symmetry. So you don't know what to take. Like if you consider this is the background, there should be some perturbation, okay? The harder part for this problem is to write down these perturbations in a good way so that at the end of the day, when you go to field equations and solve them, you will have, solvable system, okay? If you consider the symmetry is well enough, you will have all the equations decoupled, okay? Nicely decoupled, and you can solve them. So let me show you what a mu perturbation is. And this looks really nasty, but there are a lot of functions that looks free, right? H's, B's, and C's, and A's. And there is also some background symmetry for it. But the trick is when you write this in the flat coordinates, it is actually really simple because when B, C, these are the perturbations, remember. So when I go to infinity, these will go to 0, okay? So you just write down these perturbations and plug in the action, okay? Just to see that your action stays finite. If you have written the perturbations good enough, you will just have these scalar, so-called the scalar pieces of the perturbation, meaning the traces and HTT ones. And you go to the stress energy complex and plug in your perturbation again, you will find some stuff. But these are still in covariant form, and I didn't solve the field equations for the perturbations, okay? Now if I consider constant perturbations, meaning that are constant in boundary direction, so there is no time thinking in here, okay? There's no time dependence. So, and since there is no time dependence, you can write the perturbations in this way, again, considering the symmetries and so on. This is quite standard in cosmological perturbations and so on. You can go and check those from those lecture notes, and you can apply those lecture notes to your problem. And what you need to do is just to solve these field equations. Okay, these are all perturbations, and although they look quite complicated, this is a linear system and it can be solved easily. Then you will find your perturbations, and the rule here is the solutions. You should choose the solutions that respects the asymptotically Lipschitz conditions, meaning at the infinity these guys should not blow up. So you kill the blowing up guys, like C4 is constant at infinity, it can blow, and like there is here, this one also blows up and you kill this and so on. So at the end of the day, if you take the ones that are satisfying Lipschitz condition, you will find the value of the action will be finite for the perturbations. The energy will be finite. Okay, that's a good indication that you are on the correct way. And yeah, I will just skip this one. And you can do the same thing for the vector modes and so on. You just solve the same thing, go through the equations and so on. And you will find that the energy flux and the momentum density as follows. And these are still finite, which is good. And for the tensor modes, again, you go over the tensor modes, solve them, and you will see that this spatial stress tensor is as such, okay? Although it looks complicated, these are still finite and still it is good. But you need to show that these satisfy the diffeomorphism or word identities for the boundary theory, right? So if you remember, word identities are as follows, like this, right? These time derivatives and so on. But at the first part of the paper, I studied these time independent ones so that these are trivially satisfied. What I need to show is this guy, right? The second guy. So you can, from the computations I have done, you can show that this z times epsilon is satisfied. So everything works fine. And in order to check the other word identities, you need to consider the time dependent perturbations, but which I don't go into details. And yeah, that is the perturbation piece. And I will come to the numerical black holes if I have time. How long do I have? 5 minutes?
5 minutes, yes.
Okay, for the numerical ones, this is quite easy to study actually. So the numerical, the black holes are important in Einstein-Young means because, as I have written here, when they are first found, they were quite surprised because there is desert proof of no static solutions in Young means, and there is Lihornev's theorem that no gravitational solitons. So these two suggest that there are no solutions to Einstein-Young means system that particle-like solutions, right? But when first found in this paper, it was quite a surprise. Then later, the numerical ones are found, okay? And these are the references. So on the Lipschitz side, I constructed in the previous paper, first the background, then the numerical black holes, and they were quite different than the ADS ones, and there are some differences for them, but I will just skip them. So in order to find the numerical ones, you just write down the background solution you find and plug in f and g unknown functions here. Then you go to the field equations, and there is some message here. So there is some, you need to define some extra functions so that you take your boundary value problem to an initial value one, okay? These 4 equations are initial value equations, and you can solve them numerically. And numerically by mean, so at the end, all these functions, f, j, g, h, will numerically go to 1, okay? When they are 1, you will have the Lipschitz background and you have the solution. And you also need, it is helpful to plug in the horizon series for this expansion, and you can numerically integrate these functions and show that starting from some horizon, they all go to 1, okay? This hj go to 1, this gf go to 1. So you have the solutions for different z values, okay? And the behavior changes. With the black hole solutions, you can compute this is the second part of the work. So you can compute the energies of the, and the spatial part of the black holes, okay? So the good thing is they are finite first. So you can compute E. As you see, it starts from some horizon and saturates at some bound. So the energy is finite, which is pretty good. So, and then you can find this pi xx and the spatial part, and you can check this word identity, right? Z times epsilon pi, this scaling identity holds for these numerical solutions. Finally, you can also show that these thermodynamically, these black holes should satisfy this smart relation and the first law, okay? This smart relation is kind of different than ADS ones, but in this paper, it is quite well studied, so it is well known. And there is this first law piece here. The first law, from the first law, by working out the first law, you can show that this energy scales like R0 to the Z plus 2. I mean, the R0 is the horizon radius. So energy scales like the horizon radius to the Z plus 2. And by studying the numerical solutions, you can show that this energy that we have computed is actually scaling like this R to the Z plus 2, because this axis is the horizon and this axis is the energy. And this is the fourth order, this is the fifth, and this is the sixth order polynomial. So everything works fine. And at the end, you need to compute, you need to show that Z plus 2 epsilon is equal to 2TS, which is the smart relation. And you can show that this is also satisfied by just taking the different values of Z and compute all this stuff from the known quantities we have, numerical ones, and show that their ratio is the same, right? Because I didn't set them to, I mean, there could be some numerical constant that I forgot, but it is enough that they should be the same. Okay, so with this final result, there is something important I have shown. Actually, these numerical black holes I have found before have Hairy, right? They are Hairy solutions because they're like here, the smart relation, they have this smart relation here, or this first law here, and in nowhere I have this charge, SU2 charge, right? So at the infinity, this SU2 charge doesn't show up, so it doesn't affect the thermodynamics. So these are Hairy solutions. Okay, that is the conclusion. I will just give you the shortly, and yeah, what we have done is just compute this stress energy tensor complex for the Einstein-Young means, and I have shown that these, for the linearized solutions, everything stays finite, so things are working well. And as a final check, I have shown that these thermodynamical quantities obey the first law and smart relation. And there are a lot of future directions, but for now, I don't need to talk it about. I don't have time. So thank you for your listening. Okay.
Deniz, thank you so much for this great talk. Do we have any questions from the audience?
Sorry about the Wi-Fi, by the way.
Oh, no problem at all. We are grateful that you are joining us from China. I mean, it's a long distance. Okay, then I'm gonna stop the recording.